Okay, welcome to example number 14. We have a Kirchhoff's rules problem, and we have two resistors with two batteries and one single circuit. So in this type of problem, our first step is to draw a large circuit diagram, and there's a circuit diagram drawn here. We want to make sure there's lots of room when you draw these circuit diagrams, so you have plenty of room for the labels. Okay, so we want to label all the quantities, so I'm going to just call this 6-volt battery EMF 1. And then this first resistor of 4 ohms, we'll call that resistor 1. And then the 9-volt battery we'll call EMF 2. And then the 2 ohm resistor we'll call that resistance 2. Often you won't know in advance what the actual direction of unknown currents and or EMFs. But this doesn't matter. You just carry out your solution using the assumed direction, and if the actual direction of a particular quantity is opposite to your assumption, the result will come out to a negative sign. So if you use Kirchhoff's rules correctly, they will give you the directions as well as the magnitudes of the unknown currents and EMFs. And if you just have the wrong direction of the current, you just get a negative answer for that. And same thing would apply for EMFs. But if you look at this problem carefully, you could probably accurately decide what direction the current is going. You see that there's a 9-volt battery that is pushing this current counterclockwise, and then there's a 6-volt battery that's causing the current to move in the clockwise fashion. And in fact, since this battery is a larger EMF than that one, that would cause really a net EMF of really 3 volts. And I'll talk about that other alternative solution that you could do this problem. But this problem is really to illustrate Kirchhoff's rules. So since this battery has a larger EMF, let's assume that current is going counterclockwise. So here we'll draw I all the way through here, and actually so that current would be being forced through this battery in the opposite direction. Okay, so we've labeled the currents, or the current, and we've labeled the resistances and the EMFs, and we want to start off by, if there was a junction, we would apply the junction rule, but we don't see any junction. So in that case, we'll skip that step, and we'll move into the step of applying the loop rule. So we look for some closed loop, which we have one entire closed loop, and we want to designate the direction, whether it's clockwise or counterclockwise, and how you will go around the loop when you apply the loop rule. So let's go ahead and pick a direction. You could go counterclockwise or clockwise, it really doesn't matter. Sometimes I will label points here. I'll label that point A and B here, and then C and D, so that when I start part A, I could say, here's what I'm going to do. I'm going to look at loop A, B, C, D back to A. Alternatively, you could simply just draw on your diagram the actual loop that you're going to traverse. So this is our direction we are traversing around here. So now we're ready to apply Kirchhoff's loop rule, which is the algebraic sum of the potential differences in any loop, including those associated with the EMFs and those resistive elements, must come out to be equal to 0. So the way we write that is the sum of the voltages equals 0 for around basically a loop. So remember that when you apply that loop rule, you have to remember some of the sign conventions that we utilize. So let me just review that and go to the previous page. So the sign convention for resistors would be, if you traverse a resistor in the opposite direction of the current, then that would be like you're going uphill. You're going up the waterfall, as I was showing earlier when we talked about circuits. If you traverse a resistor in the same direction as the current, so the current's going to the right, I'm going to the right here, then it's like you going down the waterfall, so you're going to be losing potential as you fall down the waterfall. Now with batteries, as you traverse a battery from the negative to the positive, you are in fact increasing your potential. So you could think of it as like you're going up those steps up here, and so you're going to be going uphill. And if you go from the positive towards the negative, then it would be like you're going down the steps, and so you're going basically downhill. And so that potential will be a negative drop. Okay, so we're ready to apply that loop rule now to our circuit, and as we go around this loop A, B, C, D back to A, we will first traverse this 4 ohm resistor in the opposite direction of the current. I'm going to the right, but the current is flowing to the left. So that first term is going to be going up the waterfall, so that's positive I times R1. That would be the voltage increase as you go from A to B. And then as you go from B to C, you're moving over the battery, starting from the positive and going towards the negative. So it's like you're going from the top of the stairs and all the way down the bottom of the stairs. So that would be then a drop in that EMF2. And then as we move from C to D, we are going to the left, but the current, remember, is going counterclockwise, which is to the right here on the bottom side here. So therefore, once again, you're going up the waterfall. So that would be an increase of I times R2 of a voltage for C to D. And lastly, as you go from D to A, you are going over the battery from the negative to the positive. And once again, if you look at this, you're going from the bottom of the stairs towards the top of the stairs, so you're going uphill. So this is going to be an increase in that EMF. And then you get back to A, and you know that all the sums and subtractions of those voltages will basically add up to 0. So now we're ready to substitute in here. We have I times 4 ohms. We have the EMF2, which is 9 volts, plus I times 2 ohms, plus the EMF of 6 volts. So we can see that we'll have a net voltage of negative 3, which when we bring it over to the right side, we'll have 3, and we'll have a total of 6I on the left side. So if we divide by 6 both sides, we'll have 3 over 6, which is basically 0.5 amps. Now, alternatively, just to show you, if we had done, say, the opposite of the loop, and we went from A to D to C to B to A, just so we could discuss that, then what you'll see is as we go through here, we start from the positive towards the negative. That would be a drop in EMF1. And then you would be going down the waterfall. So that would be then a drop in voltage IR2. And then you'll be going from the negative to the positive. So that would be an increase in EMF2. And then as you go over the last resistor here in the direction of the current, that would be a drop in that potential IR1, which is equal to 0. So once again, if you look at here, this line and this line are very similar. The only difference is where you have a plus, for example here, this is a minus, and where you have a minus, you now have a plus. So it's just really simply change the same direction, just change the signs. And you will end up basically getting the same answer alternatively. Okay, so now we want to draw the graph of what the potential looks like as we start the circuit, and we assume that V equals 0 at the negative terminal of the 6-volt battery. So basically, if I put a little point here, that potential at that particular point is 0. And what we want to do is we want to show what the circuit looks like as we go across the circuit. And we obviously have to pick a direction that we're going to be moving at. So I'll assume that we'll go same thing as clockwise. So we're going to go from that particular point up to A, B, C, D. So if we start here and we look at this, we're going to start at the negative terminal and we're going to go up to 6 volts. So here we are. Okay, and that is basically at point A. Then we go over that first waterfall. And actually we're going up the waterfall because remember that we're going against the current flow. So that is going to be an increase of 4 times the current. So that 4 times the current, 4 ohms times 0.5 amps gives you 2 volts. So then we're going to go up another 2 volts right in here. So this is like point A here. And now we're just got to basically point B. And then we get to the top of the stairs, and then I'm going to drop by 9 volts. That means that if I drop by 9 volts, I'm going to go down to -1 volt. So right roughly here, I will have now this point right here, we'll just call that point C. And so now we're at point C, and then we go up this resistor, which is 2 ohms here. And 2 ohms times 0.5 amps is basically 1 volt. So we're going to end up right here. And there's point D. So you'll see that as I went up 6 volts first time, and then I went up another 2 volts, and then I went down 9 volts, and then the last bit over the resistor we have a potential increase of 1 volt. Whoops, 1 volt here. Okay, so that's the graph for example 14 and showing how we found the current for this circuit using Kirchhoff's loop rule.